So this is lab number 7, and let me start with the simplified LTE systems. As at the beginning of the labs, in the lab number first, I had given you the outline of all the labs. So we already covered the basics of the signals, then we covered the end-to-end communication system. So we saw how the signal is generated, and then when it is propagating, how it encounters some noise, and how it is modulated, and how it is all the process is happening to the systems, to the signal, and when it is received at the receiver, then how we remove the noise terms and how do we recover it. So all those details we covered in the previous labs, in the past six labs. So in the lab 7 we are starting some new lab, and this one is the not end-to-end communication system, but let me take the laser first. This one is the simplified LTE system. So the first part contains the random binary sequence generation and then the channel encoding. So we are going block by block, and we are trying to understand how the simplified LTE system works.
So let me begin with the basics of LTE. So in this lab, I'm not going deep into detail of the various architecture issues and a lot of things related to the LTEs, but I'll be giving you a very um, abstract touch of the LTE. So I want to explain you how the LTE works and how this LTE is necessary in our daily lives, because previously we were having 3G system. Before 3G we were having 2G system. Before 2G we were having 1G system. So why this generation of the systems are coming, and why our LTE is getting evolved? So let's begin with the very basics. Before we were having the very basic system, which was the 1G system, and 1G system was used for only for the voice, or which means that it was used only for the calls. Then the 2G system evolved in our labs, and the 2G system was not only capable of voice, but it was also up to some extent used for the data purpose, which means the internet. But the internet speed was very limited. And then the 3G system came, we saw it in the 2010. We saw a lot of a mobile smartphone came in, and they were supporting the 3G system. And that was not only using the voice, it was not only supporting the voice, but it was using, there was a tremendous improvement in the data rate as well. And the internet was quite improved in the 3G system. And then in the 4G system, the 4G system was the advanced version of the 3G system, far more advanced, because it completely changed the architecture of the 3G system. And it was not only improved in terms of the voice quality, but also there were a tremendous improvement, a lot of improvement in the data rate. Okay, for the data rate, they did two things. They were focusing on two things. They were firstly uh, in the data. Sorry, this is not data rate. This is only data. They were firstly interested in improving the throughput. Throughput means the data rate, and they were also interested in reducing the latency. So why was the throughput important? The throughput is important because if you're using the internet and you're surfing any website, or you are even using your voice wipe application or anything, you need a very high speed internet nowadays. Or if you are watching Netflix or anything on YouTube, you need a high speed internet to avoid any kind of buffering and those um, slower internet problems. So you need the high throughput. Then what is the latency? Why the latency is important? The latency is important because most of the household elements or many of the devices nowadays are the IoTs. So IoT means that they are Internet of Things devices, and the lighting or the lighting level or the room temperature, or most of the things are connected with each other through the internet. Are all those devices are then connected to some intelligent system, and that intelligent system is controlling all those devices. So, to control each and every device in real time, there should be a very low latency. So, it should not take seconds, it should take milliseconds, or it should take even nanosecond or microseconds. So, it should take a very less amount of time to do any control, to send any control commands. So, for the IoT devices, the bandwidth is not that much important. The most important thing is the what we call it, latency. Latency is very important for the IoT's devices. The bandwidth is less important because IoT devices, they don't send a tremendous amount of data. Like they all together sends a lot of data, but each and every device needs some commands to be operated. So some turning on, turning off, those kind of command, raise your level, reduce your level, keep on this level. So those kind of commands should be transmitted instantly between the IoTs or to the IoTs. So the bandwidth is not that much important as much the latency term is important. So the 4G was interested not only to improve the throughput but also to improve the latency. Now let's come back to the 4G system. Um Why was the 4G system so important? The 4G system was important because uh, the people who are stationary, and then the people who are mobile, they have in the 3G system, their throughput was still better, but not that much good. The stationary mean when you are sitting at home, you are not doing anything, then at that you're just are walking very slowly. That kind of situation is stationary, and stationary means that you will have a high throughput, high data rate. But when you are mobile, then you will be having a lot of other uh, some channel degrading phenomena is happening there, and then you will have a considerably lower uh, throughput at that time. Okay, now the as I told you, two things are very important. The one is the latency, and the other is the throughput. To increase the throughput, you need to send more bits per symbol. What does bits per symbol mean? What does this thing mean? For example, this is your n phase and this is your quadrature phase. This is kind of your quadrants, and you have to separate your data bits. So previously in the previous lab, you saw that we used the BPSK, right? BPSK, we already saw it in the previous lab, and you are having two states only. You are transmitting 0 or 1. So when you are transmitting 0, you are starting from minus cos something and you are using 2 cycles. But when you are transmitting 1, you are doing the opposite way. So it means that you are having only two states, which means that you are having this state and then you are having that state. So when you are sending 1, you are using this quadrant, and when you are sending 0, you are using that quadrant. But nowadays, the story is a little bit different because you are not only using this one and this one state, but you are also using within the same quadrant, you are sending a lot of data. Because you need to transmit to increase the throughput, you have to transmit many bits. When you are transmitting many bits, then you need some space, and within that space, you have to send your bits. So if you look at here, for example, this one, this is, for instance, we call it QAM modulation, and then how much bits are per quadrant? This is 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. So which means that it is 4 QAM. And if it is 16, then there will be 16 over here, and 16 here, and 16 here, and 16 here. If it is 64, then there could be 64. And it can be as much as 256 or 1024. So to increase this throughput, it means that you are increasing the spectral efficiency, which means that you are sending more bits per quadrant. When you are sending more bits per quadrant, then this is, for example, your transmitter side, and then when you are receiving them, they should be uh, received at the proper position. For example, you transmitted this bit here, it should be received here. You transmitted this one, it should be received here. You transmitted this one, it should be received here, and this one should be received here. This one should be received here, and this one should be received here. Ideally, the situation should be like that. But practically, this doesn't happen. Why? Let me further elaborate you this story. You have a transmitter here, you have a receiver here, and then you have a lot of noising things. This is noise. And what is noise? I explained in previous lab. It can be trees, it can be buildings, it can be humans, and it can be birds, it can be anything that is striking off the signal. So the signal, when it goes through this channel, this is your channel. You need a channel for communication, right? You always need a road for driving, so you also need a channel for your communication. So this channel is full of the noise terms. So the cars or the humans or the buildings or anything that cause your signal is striking off, and finally it is reaching at your receiver. Let's suppose that your transmitter here is in line of sight with your receiver. Line of sight means that this is your channel. This transmitter can directly see your receiver, and there is no any degradation or there is no obstruction in their path, and it can directly receive here. So when the channel is in line of sight, then in that case, there is no degradation, that kind of degradation happening, and you receive the signal exactly like the way you transmit it, for instance. Or there might be some phase changes, but those will be quite negligible. And if you see it in the frequency domain, you will have the flat response of the channel, and that flat response means that you have a flat fading channel. So now let's go to the practical case. When you have a transmitter here, let's say you have a transmitter here, and then you have a receiver here, and then you have multiple channel degrading phenomena like building, trees, human, or many things. Okay, so your signal striking off coming like that, striking off coming like that, some rough road or some other scattering element. So when it strike like that, maybe multiple copies of the original signal, and then finally something like that. Anyway, when your signal is received at the receiver, there will be multiple copies of your received signal. So those multiple copies are added with each other, and when they are added with each other at the receiver side, they are added constructively or destructively. Mostly they are destructively adding, and that leads to the frequency selective fading. And the frequency domain, the frequency selective fading channel looks like this, for example. What is the difference? Okay, if you see this one signal in the frequency domain, it looks like um, this, but when you take the Fourier transform of this one, sorry, in the time domain, it looks like that. And the Fourier, when you take the Fourier transform, it will looks something like that. Okay, but when you have further degrading signal, or means that the addition of more signal, then you will have also the channel like that. and then in the frequency domain. But if you have many of the replica of copies of the signal receiving at the receiver, then you will have many of these downfalls here. So if you are using all of this bandwidth, which means that this is a huge bandwidth, right? So if you're using the whole bandwidth of the signal, for example, your signal is arriving from F0 to F1 and your mobile, this is the width of the road, for example. The bandwidth is always the width of the road, and the road is very rough because of this crust and troughs. So because of this crust and troughs, the road is very rough. So when your car is moving here on this road, it will be because of these bumps, kind of road, a rough road. Your car quality will be quite degraded if it covers, for example, 1,000 kilometer on the same road, right? So in this case, this crust and trough and this signal make your channel very erratic. This is your channel, and these kind of bumps or these kind of uh, roughness of your road will make your data, which is your car here, it will make it more and more erratic. So to make your channel flat fading, you need to, for example, use a smaller bandwidth. For example, if you use the this portion of the bandwidth here, right? This portion of the bandwidth means that for this one, this area is flat, right? Even for this one, for example, if you're using this one again for the other portion of the bandwidth, this is flat. Then you are using, for instance, this one for the other portion of the, then again it is flat. So there is another concept now. If you clearly observe this one, rather than using the whole bandwidth, which is a big bandwidth here, why don't we use the smaller portion of the bandwidth so that we have the flat fading response? We have some response like this. So in order to have that kind of response, we need to use the small portion of that road. And to use that, let me rewrite like here, for example, you have that kind of signal, that kind of uh, channel, and then within that channel, let's say you don't want to use the whole bandwidth of the road, but you want to send partially a part of your data on the small portion of the road, then another small portion of your data on the other portion of your road, and then another small portion of your data on the other portion of your road, which means that you are only using portion of this road. So ins for this portion of data, this surface is flat. Then here for the blue, this surface is flat, and then for this one, for example, this surface is flat. So in this case, you can get some flat response for every kind of the data. And here comes the concept of the OFDM signal, OFDM transmission. So, what is the main goal of the single carrier and OFDM? Let me try to make this story more simplified. You are, for example, in the first case, the red case, the red signal. Let me take the red signal, and this one is your transmitter, okay, and this is your receiver. And then, for example, the transmitter and the receiver, they are you have the data here, as I told you. You have this data, this is your data, right? So you superimpose all your data on a single carrier like that. So you put all the data here, for example, which means that the data will get very congested, and then you transmit it. It means that you are using this complete band of the road, and then within that, this signal is traveling here, and you are experiencing these selective fading channel. So this is frequency selective fading, and these crust and troughs, these crust and troughs will further erratic uh, your transmitted data.
But on the other hand, for example, you have again the same scenario and you have this data, and then you have the multiple subcarriers. For example, you have the subcarrier number one, subcarrier number two, subcarrier number three, subcarrier number two. So you are partially transmitting the data on this subcarrier, then another data on this subcarrier, the other data on this subcarrier, and the other data on this subcarrier. So you are partially transmitting, although you are doing the same thing, but you are using multiple subcarrier. In other words, you had this much of bandwidth, right? You had this much. So you sliced your bandwidth, and then you are using it for different kind of subcarrier, for different type of data. So when you transmit this data to the multi carriers, it means that if your channel response is like that, then you are receiving the signal, you are sending the signal like that. So each one of that in the frequency domain is belonging to one of your subcarrier. So this is the OFDM system basically make it, even if your bigger channel is the frequency selective, the smaller chunks of this subcarrier will make it, these bins will make it flat fading. Flat fading means that the response of the channel for the smaller portion of the for the smaller portion of the subcarrier will be selective. Will be, sorry, not selective. It will be flat fading, right? So I think it is a very complicated concept. I try to explain it in easy words, but if you still don't understand it, please try to understand some concepts related to the OFDM system and the how it works. So the OFDM is the core part of the 4G systems. The 4G systems is trying to eliminate this kind of error in the channel, and to eliminate that kind of error in the channel, the error happening in the frequency selective channel, the data is sent into multiple bins or the multiple subcarriers, and those multiple subcarrier will have the flat response even for the frequency selective channel that would be possible in the single carrier system. So this is one of the core part that we will be studying in this the OFDM system that you will be studying in future in very detail if you are in going to the communication part. If you are specializing in the communication engineering, then this will be very important part. And also, if you are doing the graduate course from here, there is a course offered called the digital communications, and you will deeply understand all the concepts related to the LTE and also related to the OFDM systems. Okay, so this was a very brief review for the OFDM systems, the frequency selective, flat fading, and also related to the throughput of the system. So in the next, yeah, I hope this is the very basic overview of the LTE basics. So in our system, we will be now in today's lab. Uh, I think I should be doing all the tasks day by day. So I'll be updating you everything related. So the previously we studied the end-to-end communication system where I explained you the whole picture in the beginning. But then I was trying to explain you again and again the same story. So this time I'm trying to only explain you the task that we are going to do each day, and then in the next day I'll be trying to just recall you what we have done on the previous lab, and then we will move forward. So in today's lab, what we will be doing, we will be generating a signal. And how to generate a signal? We are not generating a signal, but actually we are just generating the some random bits. Okay, so we will be generating the random bits, and then we will be doing some channel encoding. So in the channel encoding, there are a lot of channel encoding like um, Hemming coding, for example, or there is convolutional coding or turbo coding. There are a lot of other coding, but we will take one of the very simplest one, the Hemming coding, and this is the task for today, and then we will move forward to the task.
So the goal of the lab is firstly to generate the binary sequence. And once we generate the binary sequence, then we will be doing some the channel encoding technique. We will be applying the channel encoding technique. So let me first make a new file here, and I'll save that new file with lab name, for example, lab 7. And from here I'll start with the CLC, close all and clear all. So these three lines are very important, as I had told you at the beginning. And after this I'll start the lab. So the first part is to generate uh, the random sequence of bits. So in the MATLAB there are some built-in functions, so you don't have to worry about the making it by yourself, because it's not so easy to generate the random sequence. They are using some Monte Carlo technique, and a lot of algorithms are running behind it. But when you see it, for you it's so simple. You just use the built-in function, and that can work for you. So firstly I want to, how much number of bits you want to generate. For example, total bits, I want to generate the total bits up to 4096, which is almost 4 kilo. I want to generate 4 kilobits, and to generate it in a binary form, I'm calling it source mm, bit is equal to, and then there is round. I'm putting the round because there might be some uh, yeah, I'm putting the round. If there is some fraction, it should remove it, and then I shall say that rand, what is the from 1 to this bit, this total bits. And after this I'll just simply run it, and you can see that it has generated almost 4096, not almost, exactly 4096 of bits. So already my source bits, and this variable contains the 4096 of the bits. Now my bits are generated, and the next goal is to apply some FEC coding. So the goal is to show you the basic encoding, channel encoding technique, and from here the Hamming coding I'll show you. Before going into details about the Hamming coding, let's first see in the drawing how the Hamming coding works, and from the Hamming coding details, then I'll explain you this in the coding.
So before explaining you the channel encoding, I'll just firstly give you a brief review related to the parity bits. So, as I told you, you have in the digital communication, you have a transmitter and then you have a receiver here, right? So there's data in the digital form, the digital bit that we just generated. It is in the form like, for instance, 1010. I'm just let me take an example of 4 bits. So this is your digital bits, which is generated from the transmitter, and then you have some erratic channel here. So then these bits are transmitted over this erratic channel, and when they are received here at the receiver, the bits may not be properly received. It may or may not be properly received. It may be received properly, for example, correctly as 1010, or it may, for instance, not received correctly, it may received as 1011. So this one was supposed to be 0, but it received as 1. So this kind of, for instance, when you are sending your bits from here directly to the receiver without doing anything, it means that you are sending your data uncoded. But what is the pros? The pros is you will occupy less channel bandwidth. So less channel bandwidth means that you are saving the channel, the bandwidth of the channel. But what is the cons? Cons is when you are transmitting your signal without coding it, then because of the erratic channel, some bit may be flipped or some bit will become erratic. And when your bits are becoming erratic, it means that whatever you have transmitted, although you saved the channel, you saved the bandwidth, but what you transmitted, it is not what you have received. So the transmitted is not equal to the receiver is received bits are not equal to the transmitted signal, which means that whatever you have transmitted, the data has been corrupted at the receiver. So when the data is corrupted, then there is no mean of doing any communication because you say hi to some person, but that person is listening it as bye. But the meaning is quite different. You are saying hi, and that person is listening it as bye. So it means that what you said and what he received, they are totally contradictory. It doesn't make any proper coherence. So that's why we have to do some channel coding. For the channel coding, what is the purpose of the channel coding? The channel coding purpose is to, even if some of the bits are flipped or it is erratic, some error is added and they flip or bit or make it erratic at the receiver side, it should be recovered again and because of the channel coding. So the channel coding will occupy some portion of your bandwidth, but what will be the reward? The reward will be, even if you have some errors, it will recover the errors. Now let's come back to the parity bit. Parity bit means that along that 1010 signal that we considered just here, so this signal along with this one, you are sending some parity bit. And with this parity, you are 1010 is received, and the receiver knows what the parity is. So the parity is the role is to detect if there is error or not. The parity can be of two types. It can be odd parity or it can be even parity. So if it is odd parity, then in that case, the number of ones, the total number of ones in the transmitted signal along with the parity bit should be even. Sorry, if it is odd parity, the total number of ones transmitted in a from the transmitter side should be odd. For instance, I have the 1010, so 1 2. They are even. So to make it odd, my parity should be 1. So now this kind of parity is called odd because this parity make the total number of 1 is odd. 1 2 3. I have 3 ones here. But if your parity is supposed to be even, then if you have the same signal like 1010, then in that case, the parity bit should be 0 because the total number of 1 should be even, which is 1, 2. So in that case, it is even parity. So in case of odd parity, the total number, the data bits, these are the data bits, and this is the parity bit. So the data plus parity bit, the number and that should be odd. So the total number should be odd. On the contrary, it should be even for the even parity. So I hope this is now very clear, the role of the parity bit. Now let's move forward to the Hamming coding. So let's take this example. Let's not forget this one. So I have 1010 to transmit using the Hamming coding. So in ham encoding, there is something which is called the block length. So the block length is something like this, where you have the data and the parity altogether. So for instance, let's say how much should be the block length. So the block length, which is generally denoted by n, it is equal to the 2 power r minus 1. And this r should be greater than 2. At least it should be greater than 2. So for r is equal to 3, if I put it in n, then it should be 2 power 3 minus 1. And this should be 8 minus 1 is equal to 7. So the length of this one should be at least 7. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now my length is the length of the parity bit is 7. Now let's check if I have the length of, if my n is 7, I have to verify that what is the message. My message is 4 bit, right? So I have to verify that the message should be 4 bit only. So to ensure to derive the value of r is we have r is equal to 3 for this case, right? So let's keep it in the message. So we have the formula. Let's say for k is used to denote the message. K is equal to 2 power r minus 1. So this is the formula to compute the message. So if I put the value of r there, 2 power 3 minus 3 minus 1. So 8 minus 3 minus 1. So 8 minus 4 is equal to 4, which means that my message length is 4. So it is correct, which means that the R value which I assumed here is correct. Or if it was not correct, I would have increased R further. For instance, the minimum should be 3 and the maximum should be as long as you go. So it could be 4, 5, 6, 7. Okay, so now I have the 4 for the message and the total number of blocks. Now it means that the message is 4, the block length is 7. So what should be the parity? The parity means that t is equal to n minus k, which is equal to uh, 7 minus 4, which is equal to 3. So total number of parity will be 3. It's very evident, right? If you have the total block is 7, if the total block is 7, the message length is 4. Of course, what remains is only the parity. So the parity is only 3. Now let's move to how can we do the compute the parity bit. Let me redraw that figure again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay. So yeah, how to put the parity position and how to put the data position. Actually, there are some rules to be followed for the ham encoding, and to arrange the data and the parity, we should follow those rules. So arrange the data slash parity. So the rule number 1 is uh, the parity is, for instance, 2 power n. So 2 power 0, where n is equal to 0, 1, 2, up to, let's say, capital N. So 2 power 0 is equal to 1, 2 power 1 is equal to 2, 2 power 2 is equal to 4, 2 power 3 is equal to 8. Do we have 8? No. 1, 2, 3, 4, 5, 6, 7. We don't have 8 position here, right? So since we don't have 8 position, so we should discard this one. Now, what is the parity? The first parity position, this is here. P1 is here. What is the second? It is here at 2. What is the third one? It is at fourth position. So we have the parity position P1, P2, P3. What was our data? Our data was 1010, I guess. Yeah, I think. Yeah, it was 1010. So let's say this is my D1 this is my D1, this is my D2, this is my D3, and this is my D4. So the D4 is this one, D3, D2, D1. So 1, 0, 1, and 0, right? Now let's compute the parity bit. So the rule number 2 for computing the parity bit, and it is like this. For the, I'll just simply put 3 lines, P1, P2, P3. So if it is D1, D2, D1, D2, D3, and D4. So for the P1, it should be P1 has the parity from D1, D2, and D4. P2 has the parity from um, D1, which is this one, and then D3, and then D4. And then P3 has the parity from D2, D3, D4. Right? So if we see the bits order from here, let's say I'm using the even parity, right? So you already know what is the even parity. So my P is even. So what is D1? D1 is 0. So D1 is 0. What is D2? D2 is 1. So D2 is 1. And what is D4? D4 is 1. So what should be the parity? Since the parity is even and the number of the ones are already 2, so I should just keep the parity bit as 0. Now the total number of ones are 2. That's why it is even parity bits. Now let's consider the other one, which is the um, P2. So P2, what is D4? D4 is 1. What is D3? D3 is 0. And what is D1? D1 is 0. Now there is only one here. So to make it even, my parity bit should be 1. So the total parity are now 2. Now for the P3, if I look at here, it is D4. So I think it's like that. Two ones there, so I should have it 0. But if I was doing it for the odd parity, it should be reciprocal 1, 0, 1, 1, 1. Sorry, not 1, but 0, 0, 0, 1, and 1 and 1, 0, 1. So for the odd parity, I have how much ones here? 1, 2, 3 odd, 1 odd, and 1, 2, 3 odd, right? So since we are not using odd parity, so let me erase this one. I should only keep the even parity. Now, it's always almost known that what is the value of P1. So I should just plug the value of P1 here, P2 here, and P3 here. So let me read right. The value of P1 is 0. So I shall put 0 here, and like that. The value of P2 is 1, so I should put 1 here, and the value of P3 is 0, so I should put P3 is here. Now the total block to be transmitted, it is 1 0 1 0 0 1 0, right? So this is the total block to be transmitted, and it should be like this. And out of this total block, my meaningful bits are this one and this one. And what are these? This one and these two are the parity bits, right? So this has to be transmitted, and once it is transmitted on this transmitted side, the parity is known by the receiver, and it should be checked with the reference parity, and it should understand there is the it is received correctly or not. Now, let me corrupt my bits. For instance, I am transmitting the bits which is transmitted from here, but when it is received because of this erratic channel. So some error happened to this one, and it is received like this 1101. Let's say I'm making it 1 this bit and 10. So this one is now corrupted. Okay, so how do we detect it? Firstly, we have to detect it, and then we have to correct it, right? So to detect it first, at the receiver side, as I told you before, the receiver knows the parity bit. So the receiver has the knowledge of P1 is equal to 0, P2 is equal to 1, and P3 is equal to 0. Once these bits are arrived at the receiver, then what happened there? So P1, it is 0. Okay, so it will check for the P1 bits. I think I should redraw it. Let me redraw it again. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and one more, 7. Okay, to redraw it, I think this was the corrupted version of the bits for 101, 1110, 111, 0. So 101, 101. Sorry, I forgot it. 10. Sorry, I think I. Yeah, no. It was one, not this one, because it was I sent 11010, right? So it should be like this. This is the corrupted version. So this bit is flipped here. It is 1. So 1010110. 1010110. So this is what I received. And this one was supposed to be 0, but I have received it 1. So what is D1? D1 is this one, D2 is this one, D3 is this one, and D4 is this one. What is this? This is P1, this is P2, this is P3. Now for the P1, P2, and the P3, let's compute it, the parity bits. The P1 has this sequence, right? So P1 has this sequence D1, D2, D4. So I'll take it here, D1, D2, D4. P2 has this sequence D1, D3, D4. D1, D3, D4. And the P3 was D2, D3, D4. D2, D3, and D4, right? And then this is P1 parity. Okay. So what is D1? D1 is 1, so 1. D2 is 1, so 1. And D4 is 1, so it is 1, right? Now, what is in the P2 case? P2 case has D1, which is 1, D3 is 0, and D4 is 1. And then in the D2 case is 1, P3, sorry, P3 case is 1, 0, and 1. So to get a parity bit, 1, 2, so this should be 0 at the receiver, this should be 0 at the receiver, and this should be 1 at the receiver. What was the reference parity that was sent that the receiver already knows? The receiver knows that P1 was 0, P2 was 1, and P3 was 0. So 0, 1, 0, 0, 1, 0. So this is correct. This is correct, but this one and this one is wrong. Why wrong? Because D1 is involved here, and D1 is involved here, and D1, which is this one, is corrupted. So, what is the correction? Now we detected where the error is. The error was here. Okay. So to correct the error, we should add the P2 position plus P1 position. What is the P1 position? P1 is at position number 1, P2 is position number 3. So 1 plus 2 is equal to 3. So what is the third position here? 1, 2, 3. The third position is this one. So it should be flipped to 0. And this was the correct version of the transformation. So now the correct version should be 101010, which is the same as the one transmitted. Now, this is very clear now. And please remember that the drawback of the Hamming coding is the Hamming coding can only correct up to 1 bit. So it cannot correct more than 1 bit per sequence. So for each block, it can only correct up to 1 bit. But if there are 2 bits corrupted, then the Hamming coding cannot correct. And then there are more sophisticated coding techniques like the convolutional coding or the other turbo coding. They are very robust, and 4G actually using those robust kind of coding schemes.
Now let us start from the Hamming encoder. So as we saw, the message length, the block length, we will set it as 7, and the message length, which is k, we will set it as 4. And then we have to produce a generator polynomial for our cyclic code, and to do that we have the POL, which is equal to um, the command is cyclpoly, and then put the input parameters here, so n and k. So it will take the n and k and it will generate the corresponding polynomial for the Hamming coding, and we need those polynomials to properly generate the parity check and also the generation matrix. So to produce the parity check and generator matrix, we should use another command, which is let me call that one as the permat is equal to cyclgen. So this command is used to generate the parity check and also the generator matrix, and this takes the input argument, which is n, and the polynomial that we just generated. And after doing that, we will convert the parity check and the generator matrix, because the directly this form cannot be taken by the Hamming coding built-in function. So for that we have to make it compatible to the Hamming coding function, and there is a command which is the gn2par, and it will just take this function which is we generated here, and oh should here, and I'll put the semicolon, and let me call this one as the generated matrix. So this is all we need for the Hamming coding input argument. Now we are good to go. We just imply the Hamming coding, a linear coding, and that will be taking the encode. And what we are going to encode, we are going to encode this source bit. So we will take the source bit as an input argument, and then we should put the n and k as the input argument, which is the block length and the message length. And we should also put a constant here. So there are several types. If you see the help of the linear coding or the help encode, if you just type it, or you just search for the encode in the network website, then you will see that there are various ways to do the encoding process. So I'm just choosing the linear one. So you can, instead of linear, I think there is also the Hamming. So let me show you how it is done. So encode and then network. So block encoder, and there is error y. Okay, so this is what we have, and there should be some details. Yeah, you have to read these details, how to generate the encoded input. Uh, So there was some input details. Yeah, let's keep it the way. I think there is also a way. Let me check it here. Uh, Let me check it. If it is not working, then we will write the alternative one. Hemming slash binary, comma, genmed. So if there was error, then I will change this command. Not n where I used capital N. No, it is small n. And then, so, okay. I think hemming is not there, so I'll just use the linear. Okay, that's it. So it already worked, and so far it has generated the linear code for what we wanted to. So it will not make any sense for you, but to make it easier to understand, you had 4096, which are your desired bits, but it is increased by 7 times. Like before it was 4 kilo, but now it is 7 kilo. 7 kilo means that 3 kilo of the parity bits have also been added to your binary sequence, which is your source bit. So the source bit not only contains the information bit, which is here, but it also contains the parity bit, and also the yeah, but it also contains the parity bit, and the total which will makes you this one, 7168, almost 7 times of the 1 kilobits. This was 4 kilobits we already transmitted. So I think that is it for today. But before leaving this lab, please, uh, I'll ask you to go through these functions. Go to the MathWork website and understand why I use this one, and this one. Understand it in detail because it has some purpose, and try to map it with the theory that I already explained you. And then in the next class we will be covering the other blocks. So thank you so much for having your attention, and I'll see you in the next lab.